In this video, we'll cover organic isomers. Isomers are compounds that have the same chemical formula, but they are different in structure. So something that is like C6H12 and another C6H12, they have the same molecular formula, but they look completely different. And isomer, there are different categories, structural versus stereo. So we're going to cover the structural isomer first and then go into stereo. Under the isomer, structural isomer, you can see the three potential examples. All of these have 5 carbons. Okay, so this is a C5. Over here, 1, 2, 3, 4, 5, right? And all this also has 5. Now count the hydrogens. All of these guys will have 12 hydrogens. Okay, right? If you were to count all of these hydrogens here and over here and over here, there are 12 hydrogens. So they are isomers of each other in that, hey, they have same same molecular formula. The thing is, they have different connectivity, and something like this would be considered to be a structural isomer. Now, all of these 3 guys, they have different names, and also they have a different physical properties. So if you want to try naming all this, great, but this is not about nomenclature, but I will put down the name right now, okay? So the very first one, this one is a pentane. So if you want to practice the naming, okay, this one is a 2-methyl butane. And this one is 2,2-dimethyl propane. Naming these guys are in the alkane nomenclature video. All right, so these are all structure isomer. Notice that they have different connectivity, and so they have different names, and also their physical properties are different. Let's do a learning check. It says draw hexane using a line angle structure. So hexane has 6 carbons. 1, 2, 3, 4, 5, 6. So that every corner is going to represent carbon. 1, 2, 3, 4, 5, 6, right? And this has a molecular structure of C6H14. So you're going to draw another chemical, another isomer that has C6H14, but it's not in hexane. So for example, it has 6 carbons and 14 H's. It's got a methyl group on here. Okay, so this is a pentane. It has 1, 2, 3, 4, 5, right? So it's a pentane and a methyl group attached to the second carbon. So this would be 2-methyl pentane. So if you're a little unsure, you could write carbons in between right here to kind of represent all of the carbons to find all 6 of them. Now try the rest of the 3 isomers and come back and check this video. And here are the rest of the isomers. Let's do another one. Draw methyl cyclopentane using a line angle structure. Then draw 2 additional isomers. Name each molecule. So cyclopentane, that would be 5-carbon ring structure, and it's also got a methyl group. So I'm going to draw 1. Okay, so that's my methyl cyclopentane. Now I'm going to draw 2 other additional isomers. So here's one. I have a cyclobutane with 2-methyl coming out, and that would be 1,2-dimethyl cyclobutane. Now this has methyl cyclopentane has C6H12. Well, how do I know? Well, all of these corner has CH2s, and this one has just a CH, and this one has a CH3. So if I count all of the carbons, there are 6 carbons total. And then if you count all the hydrogens, there's 4, 6, 8, 10, 12. And you can do the same thing. You can actually write out the carbons in between just to double check. And then erase the carbon and hydrogen when you're done. So you're going to find one additional isomer here and come back and check this video. Now here is the key. Now you notice that this is a cyclohexane and here there's no cyclic structure. Just because you have a cyclopentane doesn't mean your isomer has to be cyclic. This is trans-2-hexene and this also has C6H12 in molecular formula. So these two are definitely not limited to just these two. There are more. It can vary, but I just wanted you to draw 2 additional isomers. Now let's go into the second portion of the isomers. So we talked about structural. Now let's go into stereoisomers. So these have not different connectivity. They have the same connectivity. They have the same molecular formula, but within the same connectivity, they got special different spatial arrangements. So for under stereoisomer, it does categorize into 2. And we already talked about cis and trans. If you were paying attention to the alkene and alkyne nomenclature. And in the cis and trans, this applies only to something with a double bond. Okay, something with an alkene. And on top of that, double bond has to be located in the middle, okay, not on the edge of the chain. So something like cis and trans, cis will have hydrogens that is either both on the bottom or both on the top where the double bond is located. For trans, the hydrogen will be in opposite direction where the double bond is located. This is a condensed structure form and this is a line angle structure form. In the line angle, you can see the trans very clearly that it's diagonal, right? There's a diagonal. Whereas cis, it looks sort of like a bucket and also it could potentially look like this too. So going upside down bucket. Okay, so that's a stereoisomer. Notice that they are same connectivity in that here's my second carbon, and that has a double bond. Third carbon, second carbon, third carbon, they also have a double bond. And on that, those 2 carbons are attached to a CH3, 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 CH3. So cis and trans, they have the same connectivities. It's just that now hydrogen happens to be here and the other one hydrogen are in the diagonal format. Now, under stereoisomer, again, I have said there's 2 categories, the cis and trans category, and there's the enantiomers, okay? Enantiomers are compounds that are mirror image of each other. So look at the compound here and look at the compound over here. Enantiomers are subdivided into D and L, and you don't need to know which one is a D and which one is an L isomer, but what you do need to know is the image on the left and the image on the right are exactly the same, right? COAH, COAH, CH3, CH3, OH, OH, and HH. So what is different is that the orientation is different, the mirror image of each other. So imagine this dashed line as a mirror image. So they're looking kind of together. Now I got a little mirror here. So imagine if there was a mirror in the middle and I put my hand like this. When I look at the mirror is not going to look like this. It's actually going to look like this, right? Because they're mirroring of each other. Even though my index finger are on the second, if I put the hands together like this, okay, together, my thumbs are kind of like on the side here. And, excuse me. And they're, and you'll notice that even though my middle finger might line up, my ring finger, and my ring finger is here. Okay, so no matter how much I rearrange it, like put your hands in a certain way, well, you might say, well, if you just go like this, they're all lined up. Yeah, but then the thing is, this one is palm facing inward, and we want to face it that way. Okay, if I face it that way, it's opposite, right? So here I have a mirror. Right? So if I put my hand right here, okay, here's my thumb. And you see the thumb over there, right? And this is what's in the mirror is actually my right hand, okay? And but it's my left hand I'm showing. Okay, this is a mirror of each other. But enantiomers are the same in that this is a mirror image of this. No matter how much you rearrange them, they will not line up together. Enantiomers must have a chiral center. What does that mean? That chiral center where that C carbon is, all around it, there are different attachment, different molecules. So this one is a CH3. This one is a COOH. OH and an H. So they're all different. So this carbon is considered to be a chiral or having a chiral center. All right, here it says draw the cis and trans of the following in either condensed or line angle structure. So I'm going to do both and show you both. Let's go with the octene. Okay, 3-octene. I'll do that one with you. So octene there means there's 8 carbons, and on the third carbon there's going to be a double bond. Here's my third carbon, and there's going to be a double bond. I'm going to draw a few more. 1, 2, 3, 1, 2, 3, 4, 5. Okay, so here's my octene. The double bond is there, and also it's in the middle. So what does that mean? This probably has cis and trans formation. So one way to write this is having the hydrogen on the same side. I'm going to erase that, and then having the hydrogen either both on the bottom or both on top. If I were to draw a trans one, then it looks very similar to this, except for hydrogen is on top for one of the guy and the other one is on the bottom. Okay, now let me draw the line angle structure. So there's 8 of them here. 1, 2, 3, 4, 5, 6, 7, 8. And on the third carbon, there is a double. Trans halves look something like this. It looks like this zigzag line where the double bond is located. For cis, remember I said it looks like more like a bucket. So here and on the third carbon, it's going to have a bucket. One, 2, 3, 4, 5, 6, 7, 8. Oh, I think I drew a little too much lines. 6, 7, 8. All right. So that's what, and let me see, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this one is my cis, and here's my trans. Okay, so this is cis 3-octene, trans 3-octene. Now you try it for the 2-pentene. And here is the key. Here it says draw enantiomer, the mirror image of the compounds, then identify the chiral center. So if I were to draw a mirror image, I'm going to go ahead and put a mirror below. Okay, let me do the first one and then you try the second one. I'm going to have a carbon in the middle and H if they were facing to each other. Well, this CH3 is going to come out that way. The other one, the OH is going to be here, and then what's going back will be chlorine. So that's a mirror of each other. Try for this one, and then we'll find the chiral center together. So here's the key. Remember, the wedges are referring to coming out of the board, and then these dashed line refers to going back. So where's the chiral center? So chiral center must be the carbon. So there's two carbons here. This one and this one for the first one. And it's going to be the one that has all four sides different atoms. So there's H, CH3, OH, and Cl. So this is going to be my chiral center. I'm going to put that as a star there. And for this one, kind of obvious one, that carbon is going to have the chiral center.